Hey everybody, welcome to the wolfSSL live webinar. Thank you for joining. Get this rolling. The webinar is wolfHSM, wolfSSL, and Automotive Hardware Security Modules, presented by wolfSSL software engineer Bill Phipps. My name is Cameron. I will be moderating the webinar. All attendees will be in listen mode only. If you have any questions, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and be made available on our YouTube channel shortly after the presentation. I invite you all to follow us on Twitter X at wolfSSL, as well as our other social media platforms. Also, feel free to email us if you have any additional questions. You can send emails over to facts@wolfSSL.com. And I'd like to give a brief overview of wolfSSL before we get into the technical presentation. Today, wolfSSL secures over 2 billion connections, and we have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we're very proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO-178 support, FIPS certification, and a FIPS ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, and commercial support for curl. All these offerings are accompanied through maintenance and support plans all the way up to the 24/7 level. We also offer full service consulting. And yeah, now I'd like to turn over to Bill to talk about wolfHSM, wolfSSL, and automotive's hardware security modules.
Thanks, Cameron. Again, my name is Bill Phipps. Been working with wolfSSL for almost exactly a year at this point. Today, we're going to be talking about where we see the HSM market going and where we think we can provide some product coverage, kind of a companion to our existing products in this space. We're going to walk through parts of the design of that today. I'll do a brief demo at the end, but I think the biggest takeaway today is to understand that we've found that we have a lot of customers asking for similar products, and we're trying our best to get a unified offering out to the market in this space. So again, today we'll kind of plow through what an HSM is and what it means in the automotive world. Walk through a couple of the things that we've been working in automotive for a long time. I'll briefly talk about some of the other products we've got and why we think a new product that kind of combines some of these technologies is the right solution for us. Walk through the functional design, explain how we handle porting from a software perspective. I'll do a short demo on a Tricore and kind of give an idea of where we see the product going, hopefully in relationship to customer needs. So right off the top, what exactly is a hardware security module? There's lots of different definitions of it, but from our perspective, an HSM gives a separate execution context that is really focused specifically on giving system level security. That may be crypto operations, that may be controlling specific IO states, it may be monitoring or strongly controlling the boot sequence. Again, the idea of an HSM core is that all of the overarching environments that you want to control from a security perspective can be contained, and you have an execution environment to do that, and you expect that environment to be running in parallel with the rest of the applications. The other key feature of HSMs that we see today are private storage and private access to cryptographic hardware. The earliest uses of HSMs that we've seen in the automotive is for things like cryptographic hardware offload. And so a bulk of the interface to the HSM was strictly done for a performance reason, as opposed to leveraging the security context that puts us in a position to execute custom code. The other thing to really think about HSM, it's the beginnings of a solution. It's a toolbox. It's not an end game. You may see commercial offerings that talk about HSMs as, oh, it's an all-in-one type of thing, and that's probably not a reality. There's a lot of there's a lot of pieces you got to put together to make sure you've got a secure solution. And we think wolfHSM is one of the ways that we can help organize those secure pieces and put them together. So, in contrast, wolfSSL has plenty of experience in other secure elements and secure technologies. And so, what I want to do is kind of point out how we see the HSM space a little bit differently than our traditional secure element spaces. And I kind of just in my chart here, just walking through a couple of the distinctions between a totally separate secure element like a trusted platform module, TPM, versus on the right-hand side, a TrustZone or a virtualized solution where it's all software based, leveraging some of the technologies that you find on modern application class processors. And HSM kind of has benefits of both without having some of the drawbacks. And by having this dedicated piece of hardware, again, a programmable security element, it puts you into a different class that you can solve more than just the bare minimum problem. So one of the issues that we see with TPMs is that you can't change the TPM code to do it what you want it to do. TPMs, you get firmware from a vendor, and maybe they upgrade it, maybe they don't. And you're stuck with that feature set that you've got. Even if you don't use any of those features, you're stuck with that set. It's also not tightly coupled in most instances to your main processor. So you've got a secondary problem. I've got to be able to talk to my TPM before I can get data out of it. From a hardware perspective, yes, it does provide hardware crypto that's in a nice protected environment, but it's not known for its high performance. So the types of jobs you use TPMs for would be initial authentication, storage of private key material, kind of the bare minimums, and doesn't quite line up, with a high performance crypto coprocessor. Of course, TPMs do provide physical storage, and they do have arbitrary non-volatile storage up to a certain size, which there's benefits. And likewise, TPMs are they can provide a tamper response if they can detect that they've been impacted. Contrast that with, again, a TrustZone or a virtualized solution. This is a pure software solution. If you're not familiar with the TrustZone, it's in essence on ARM processors, it's their offer to say, go into a different execution mode, perform your security features, and then exit that protected execution mode. Again, leveraging some of the hardware that you'll find in either the mobile series or the more complex A series of Cortex ARM processors. So from that perspective, fully user programmable, you bring your own solution into that space. They just provide the environment. It is definitely tightly coupled because it's running typically on the same core as your main applications. But TrustZone does not provide any hardware accelerated crypto. Some of the processors do have intrinsics that we've coded up and used, and those do provide that. But from a protection perspective, it's not necessarily what you would consider as a secure element. Physical protection, I put partial in because yes, you can limit memory space accesses and addresses, but you still don't have anything that's beyond the physical protection, tamper detection that you'd see like in a TPM. And the biggest downside to a TrustZone is that you don't have any non-volatile storage. If you even consider taking a look at, say, the Trusted Firmware A solution for non-volatile storage, they actually have to reach back out to a running operating system to gain access to non-volatile storage. So it's kind of upside down in that solution space. We see HSMs as kind of the middle ground that provides, hey, I've got an execution context. It's user programmable. Yes, we're going to make sure that this HSM from the hardware perspective is coupled to my applications. Hardware crypto output partial, because what we have found is most of the implementations have a limited subset of the types of crypto we need to do. So there's a need to kind of fill in those gaps. HSM implementations we've seen do have physical protection. Most of them have dedicated non-volatile storage that's separate from main flash, which is great. And most of them are or can be integrated into a tamper response system, which also kind of ties into lifecycle management and failure analysis. So moving on, we kind of see the logical space for HSMs as giving you another core to do work on, but really focus that work on the security features. From an automotive perspective, we've got a strong need to handle secure boot and be involved in that. From an AUTOSAR or a sheet perspective, there's specs that have requirements to ensure secure boot. And so we see the HSM as central and critical to doing that in a pre-boot environment and then actually post-boot to be able to handle any attestation requests that they've got. Authentication of critical code sections, obviously. In-system updates, this is a big difference as well. TPMs don't have the same necessary problem because you can't update them, but you've got, here with an HSM, you do have to handle how does the system update itself, and can you only do partial updates of application code, or just or the entire thing. So being involved in that, including rollback prevention, is definitely key to ensure that the system is viable and updatable. We also see that there's a strong need to protect calibration configuration information. And this data is not necessarily key material. It may be private application data. So we do see the role of non-volatile data storage as being expanded in an HSM, similar to the way a TPM would do, but beyond what you'd find, say, in a PKCS 11 solution, where you'd only have access to store key material. And those have to be, well formatted. Um, we do see cryptographic operations, asymmetric, symmetric, encryption hash signatures, all those need to be in there. Typically, the HSM features that we've seen on devices are also tied into the debug and the test interfaces. And so the control and disabling of those is also under the purview of an HSM. And then at the end of the day, safety critical and real time has got to be considered. So if you're considering an HSM to help to isolate your security solution, you can't forget the realities of safety critical and real time. And so that's why the design has to be a lot more complex than you'd want it to be, as opposed to just a simple secure element offload. It's more than just crypto. Logically, we see the way we've solved the HSM solution on the left-hand side is what we generally find in HSM based products, where you've got an HSM core that may be symmetric to the main application cores, or maybe asymmetric to that. It may be a totally different architecture. Tricore is a great example. You've got ARM cores here, and you've got Tricores over yonder. And so you have to handle those architecture differences specific. But the piece, or the key element from HSM is it is separate, has its own separate local RAM, typically its own separate NVM as well, has access to crypto acceleration and some other controls that may be platform specific, things like enabling, disabling debug interfaces, controlling boot sequences, features that are definitely port specific. From our perspective, we expect to boot this core using our own bootloader directly out of on-chip RAM and flash, and then start to execute an HSM server application that is going to accept requests from communication buffers that come in. And this device would also have access to a shared non-volatile memory, typically the flash that would be used to boot the additional cores. On the non-secure side, you've got your application cores, multi-core in this case. Most of them would typically have either private or segmented RAM available to them, and they'd be running, a user application that our customer would provide our interface back. We would provide a client library that links in with their user application that then manages sending the requests, getting the HSM core to do work for you, getting the response back, then providing that response back to the user application. So there's really two fundamental pieces that we see in the solution space. One is the client library that gets linked against the user application and then provides access to the HSM core itself. And the second is this HSM as a full-blown executable. We also compile it as a library, but the typical runtime is pretty straightforward. Boot up, start up the library, and that's it. So that code is not rocket science there. But again, the key feature is that all of this code that you're looking at, including platform specific code, we're involved in. It's open source on our side, and we open source as much of the vendor libraries as we can without violating any NDAs. Some of these custom controls and crypto acceleration that are done by the different vendors, they are bound under NDA. So, we've got to do our homework to make sure that we don't spill any beans that we're not supposed to. But the rest of the base logic code, again, that's open source from us, which also means you can inject your own code. If you wanted to add a new message that you wanted this HSM to do, go ahead. It's an extensible framework that you can add your own code over here to execute and do, let's say, your specific type of crypto operation or token generation or something like that. Logically, this is the way we see this, and this seems to match the available hardware. that we are mapping to pretty well. Haven't had too many surprises yet. So moving on, what have we done in the security space? If you're not familiar with this already, obviously our wolfSSL and wolfCrypt product. This is our flagship product. Again, it's a full software implementation of cryptography and TLS. Separable, of course. If you don't need the TLS layer, you can just get wolfCrypt. Very mature. It's incredibly well tested and deployed to those billions of devices that you've heard about. Some of the key features from our perspective is that we do provide hardware offloads in there. So with a single API to your crypto interface, you can do it either in software or with a hardware offload, and then you simply provide what we call a crypto callback mechanic to support that. Second product that's in this space that's related is wolfBoot. These are designed for a bare metal bootloader. It controls the flash interface in a pre-boot environment, measures applications and authenticates those. Also has access to low-level hardware crypto when necessary, and then ensures that you can support a secure boot sequence. So wolfBoot with NVM support lines really well up with the way we see HSM cores typically booting. Oops. Wolf TPM and crypto callbacks. Again, our support of Wolf TPM or TPMs in general. This provides us the ability to reach out pre-boot from even like a Wolf boot environment to access secure elements that may be less tightly coupled to the application cores. But again, it's a kind of a companion type of interface, but it demonstrates that we've been doing this type of secure element interfaces for a long time. Wolf PKCS11 is a product that allows a wolfCrypt software solution to be a responder and handle PKCS11 requests. We'll be tying this PKCS11 in with our wolfHSM client so that you would be able to do PKCS11 requests to the wolfHSM client, have it go all the way to the HSM, get the answer back, and then provide a PKCS11 compliant environment for those folks who don't have any other interface. But PKCS11 we see as probably an 80% solution in terms of the functionality that we would expect in a secure element. Specifically, it's missing arbitrary non-volatile storage. And then last thing I wanted to point out is that because some of the HSM solutions we see have limited hardware capabilities for crypto offload, this means that we need to be available to have cryptographic algorithm agility. And then I just wanted to point out, we have been implementing post-quantum and other non-NIST based cryptography in software for quite a while. So this means we could place things like ARIA or the SM Cipher suite into the software side of an HSM, and you would gain access to those features via that as well. But again, we've been working crypto for a long time. There's a lot of corollary solutions, and again, wolfCrypt has been in autos for a while as well. So we're not new on this market space. We're a little bit new into the HSM space and how ECUs and other components in an automotive have been using it, but we're catching up great, and hopefully we'll be able to solve some problems. Moving on, from an overall design perspective, we see the need for an open source solution for both the HSM server and the client libraries. Again, pointing out that some of the vendor libraries, some of the hardware we port to, have restrictions on how their technology works, and we can't open those things up to public consumption. And so we have kind of a public set of libraries and repos that we provide, and then we have private ones that once we can confirm NDA status of customers, then we zip that up and then provide that to our customers so they can grab that and continue on with the full low-level support of the hardware. We also saw the need to implement crypto in a different fashion, which is just available in hardware. Again, it may not be as fast as the hardware, but it may not have a time performance requirement, but may have a functionality requirement that simply can't be done in hardware. And again, these are extensible and able to be updated on the fly. That's the important fact of why we think software in the HSM core is so important. Wanted to maintain a common API for both our software interfaces and our hardware operations, specifically for the crypto. This makes it so that we can easily move between different HSM platforms without having to hack up a bunch of code. and likewise move between software and hardware implementation as hardware catches up and we can start to offload those things, or vice versa. We find the hardware's broken and you need a software only solution. Supporting asynchronous operations and time limit execution from an async perspective in real time. It's so important that the client library doesn't sit there and spin all day long, eating up a core while you guys are trying to get application done. So all of the calls that are done in wolfHSM from the client to the server are fully asynchronous. Put the request in, and then you can pull or get an interrupt based on status changes, depending on what model works best for you. But that's from that perspective, it was important to honor the requirement to work within real-time requirements. Static memory allocation, and then minimal uses of system libraries. Again, you won't find malloc in the code anywhere. The entire point here is the ability to pre-allocate things ahead of time, lay them out, and so you can confirm that you've got the memory you need when you need those pieces running. Of course, you can always dynamically allocate and pass to our configuration functions if you'd like to, but nothing in a startup library is expecting or requires dynamic memory allocation. Also wanted to make sure you could remove unused features. There's no reason to have features baked into your HSM taking up either flash or RAM space when you don't want them. And that also reduces your attack surface as well. So as you're doing your cybersecurity sweeps, you know that the amount of code that you've got to review is just the bare minimum of what you need to get your job done without unexpected things sitting in the back end. And again, user extensibility. This is a primary design goal. We do see other solutions out there that kind of bake in a whole bunch of kind of prefab features. We think that's not taking advantage of that execution context. It makes more sense to make it easy for the user to add and extend both the server and the client to get exactly what you need. At the end of the day, we also wanted to make sure that at any moment we had a full-blown POSIX simulator so that you could light it up on your local Linux or POSIX compliant box and be able to try out different sequences and see how things are working without having the actual hardware. So again, wanted to make sure that all the features were baked into our POSIX simulator, and also gives a good model for when you do need to port to a new piece of hardware, what are the expectations of the different bottom end functions. Again, functionally, we split this into two core chunks. We've got an HSM server executable, fully linked, that would, again, perform a bare metal startup from boot and provide NVM access. So whether that's Flash or one-time programmable stuff or some sort of custom Flash, the idea is that the HSM server executable can gain access to it, read that, configure itself, and then start to expose access to that via the client communications. We do port wolfCrypt to both the HSM core architecture as well as the application core architecture. And then, again, those can have different feature sets. So it may make sense to only do, let's say, RSA functions on the HSM. There would be no reason to ever have that. So you could compile that out of your client side library, regain that space, and whenever an RSA call needs to be made, you route that to the HSM to do that. At the same time, it may make no sense to, it's not true, but just let's say have SHA in the HSM. You're always going to be doing your SHAs locally, then don't compile SHA support into your HSM, regain that space. But we do port wolfCrypt to both of the architectures, and so you do have the availability of any crypto operations on either the core, the HSM core, or the application cores. Again, hardware crypto offloads. We do implement, let me go back, port-specific security controls. So these may be enabling, disable, debug, controlling memory translation units, whatever it happens to be. There's callbacks in there to support configuring the rest of the chip that may be very port-specific. We provide an image manager in the executable that supports a chain of trust for later bootloaders. In fact, we suspect most use cases of the HSM server is as a chained bootloader. So it'll have enough information to chain boot the next bootloader off of one of the standard application cores, and that core can then reach back into the HSM and gain access to, let's say, authentication information or key materials or even just crypto offload. Again, the idea here is that, the wolfHSM server executable measures itself. It then measures the first target that it's supposed to boot, boots that up, lets that target communicate back, and then continue the boot chain to generate this entire chain of trust. Again, we have COM interfaces for that. We do implement key non-volatile memory and other types of automotive specific protocols, like key exchanges, secure boot status. Those things are then exported and explained so that the user application can take advantage of those. The client library, on the other hand, again, we build a library, not necessarily an application, because we expect the application library to simply link this in. It does have its own version of wolfCrypt. Any HSM crypto offloads go via our standard crypto callback mechanic. And again, that lets you choose whether the local crypto is going to do the work or if you're going to offload it to the HSM. And you can do things that direction. All right, so that's functionally how things are laid out. Visually and color coded here is kind of explains how these things are tied together, what's portable and what's not, and where the logic pieces go. So fundamentally, the server executable does an initial boot. It runs through the image manager, which measures itself, and potentially the first bootloader that it's going to trigger off of one of the application cores. And then it jumps into a giant loop that's just looking for incoming requests from any of the cores that it's servicing. Again, over a local server API that provides wolfCrypt, which is a local implementation optimized for that architecture with local software crypto. It also has local access to any hardware provided crypto acceleration. Again, this is in blue, so this would be something that would be portable. As we move between different platforms, this is the piece of code that would change to gain access to the hardware crypto. It provides key management with local keys, as well as keys that may reside only in the hardware crypto or manage loading and unloading different keys into the hardware crypto. Provides a non-volatile memory manager, which locally inside the HSM flash, we provide an object-based storage with recovery. I'll get to a little bit more of that later, as well as access to any of the shared main flash that the application cores would have access to. Again, these are both blue, so these are pieces that you would port in as you go to use it. The pieces in green are the ones that are common. And then at some point, we'll be putting in authentication. The method of authentication, we haven't seen a strong path forward on this yet. PKCS11 is pins, which doesn't make sense in an HSM or an embedded environment. TPMs have a very complex method of doing authentication, so we may take a look at that. Things like TrustZone, they don't even handle authentication. So we have yet to identify exactly how we want to do that. So that's why it's marked in red. But the idea of access controls and authentication of a user are scattered throughout our architecture already. Also in blue from a port specific would be access to any hardware specific controls, IO controls, or JTAG or debug interfaces. Interrupt handling sometimes needs to be separately handled on the HSM as opposed to everywhere else. And then a sequence of flags and communication buffers. Again, these are port specific of how this HSM is going to communicate or interrupt or get interrupted by the application cores. But that's the basic structure graphically of the server executable. From a client perspective, you've got your user application code that's running. It's hitting a single API that's wrapping the wolfCrypt features that are in there, including offload for the HSM. Key management features, including, again, local key management if you wanted to go by indexes instead of by pointers to raw memory of keys, as well as to HSM client keys, which are doing remote, and NVM management, where every request from an NVM is going to go to the HSM via the communication method. From a client library perspective, just have to know how to talk to the HSM to get this working. Everything else is in essence not necessary to be ported. So the client library only has a handful of pieces that have to be ported, which is just the communications there. Other than that, this is a mostly portable component there. Excuse me. From a AUTOSAR crypto stack compatibility, we understand a lot of folks on the application side are required to use AUTOSAR. And we wanted to point out that our wolfCrypt product has been used for many years within individual crypto drivers, but we haven't seen our role as going beyond just the cryptographic until recently, where we're finding customers have stronger needs for more than just crypto. From our perspective, the way we've designed the wolfHSM, we're focused on asynchronous and abstract interface. Again, we're layered, and this does match the way AUTOSAR expects us to be coding things up. So we do expect as the wolfHSM product starts to take up more and more of that crypto stack, it's not going to invalidate the overall mindset of AUTOSAR. In fact, we think we can provide kind of a cleaner interface than what we've seen out there as well. Some of the other items to consider, what we do see in other HSM solutions, they're closed source, and any of those features that are outside of the standard AUTOSAR requirements are using custom vendor pieces, even though you've got to do the same problem, solve the same problem on multiple platforms. That really does get to vendor lock-in to the point where you can't even access certain components unless you're using that vendor's AUTOSAR interface. Um, from our perspective as well, your visibility into that driver and how it works is kind of limited to that abstraction. And so you're going to have to trust that the bottom end code that you're accessing, specifically that's running on the server, which you may not have access to, meets all the quality requirements as well. From our perspective, by opening that up, you can run, our code through your existing quality systems. And so instead of getting an assurance that, hey, we're doing things the right way, you can audit yourself and either fix it yourself or ask us to fix it, and we can take a look at moving us closer to what your quality requirements are. The biggest other item is that we find the need for things like diagnostics and manufacturing tests to be able to directly access some of these HSM features. But once you put the vendor's HSM stack in there, you don't have access to that any longer. You have to use the AUTOSAR. So by providing a secondary method, this may open up opportunities to do different levels of diagnostics in manufacturing and test. Working back through some of the base components, the important fact or the important aspects of the client is that it is basically just a communication front end to the HSM itself. Any of the additional crypto that's provided by wolfCrypt is still exposed. So simply selecting a different device ID is going to tell the wolfCrypt library whether this is going to get routed to the HSM or if the crypto call is going to be executed locally. Again, the code is written once, you simply change the device ID and move forward from there. That's exactly the goal of what we'd like to see happen. From a key management perspective, we've added additional key manager APIs that wolfCrypt typically would be looking for arrays of byte values, whether they're secret or public. And then those get passed into the algorithms. We've added the ability to provide some indirection to supply, instead of a key ID, you would subscribe to a specific key ID, potentially pass that information in, and then you can use that key ID from that point forward. And so we've extended some of these APIs to support usage of key IDs instead of raw key material. This also allows us to identify keys that are not available to the user application. So this would be keys that would exist only on the HSM. So you would ask the HSM to, use key ID number 3 or whatever it happened to be, not knowing at all what that key actually is, what the contents are. So again, the extension of our existing wolfCrypt APIs to support key IDs was what we've added in with the local key manager. And just as an example, original code would be something like this, where you've got your key, you've got the actual key material, an IV that you set up, sequence of wolfCrypt calls, initialize an AES context, set the key using the actual key material and the IV that you've got, and then you can go ahead and encrypt till you're blue in the face with using that key material and then free it off. The changes that you'd see in this case, we're identifying a key that's existing only in one of our hardware offloads. You do the initialization to identify which crypto device is doing this work. Notice on the software only solution, you said, I don't care which device it was, just use the local software. Then you would invoke this set key against this context using this key ID that's only known to this specific device. And then it's the exact same calls for the encrypt and the free. So again, it's from a code change perspective, all you really had to do is ensure that you associated a key ID with that context and then told which device had access to that key ID. So again, we're not looking to change the code very much there. This is a different example where, let's say we did know the key ID, but I wanted to leverage the hardware performance of an HSM AES offload. So in this case, you would, again, same basic code from the left-hand side where you had the key material and you wanted to encrypt stuff, in this case, you would import the key into the device after you've associated the context with the device with the key material. That would tell you what key ID to use with that. And from that point forward, you'd associate that key ID once it's loaded into the HSM with that and do all of the encryption that you want to. Again, with this AES encrypt, in this context, it's been associated with the crypto device that's on the HSM. You're off to the races. It's going to go ahead and do that offloaded, accelerated calls. And at the end of the day, the only other call we've got is to release that key that we had loaded so that the HSM can regain that. So again, minor updates to APIs to support key management. And that's really the kind of the point is kind of to help the key management of that without actually having necessarily knowledge of the keys. Moving on to NVM, this is where we found our experience in dealing with Wolf Boot specifically and a whole bunch of different types of flash systems. We found there's a lot of code it takes to be able to use flash as a reliable storage of potentially security relevant data. So what we found was being able to associate metadata, in this case, an ID number, some sort of textual label associated with the data object that you're trying to store is really key. And this does kind of line up well with PKCS11 method for doing storage of key material, where you've got some ID number as well as some label to identify the contents of that. Again, this is a generic sense. So whether you're storing private keys or calibration data or feature enablement that needs to be protected in HSM, it doesn't matter. The NVM manager is just there to store data in a reliable fashion. The key here is making sure that it's always recoverable regardless of if you lost power halfway through writing things. Some of these flash devices that are baked into these microcontrollers have limitations on the number of times you can write and the kinds of patterns that you have to use when you write to that. So it's not just arbitrary data. And plus, a lot of it's very small. So efficient usage, layouts of those is also important. From an object perspective, an object is simply just a combination of a metadata entry associated with a variable length of piece of data. We also ensure that as you update items, we increment an internal epoch counter that keeps track of the most recent version of that. And once we found a version that's intact that has a later version, you lose access to the previous one. Not necessarily having to erase it immediately. You can recover it, when you've got an opportune time to do that. But again, it's a function of making sure that you've always got at least one, the most recent valid object there. So from a layout perspective, we split the NVM into two pieces that are equal sized. We begin with a fixed size directory known at compile time, which includes a number of potentially filled entries and then free entries. At some point, we stop allowing directory entries, again, compile time set, and then you start storing data linearly into this NVM section. This allows us to have fixed size directory entries, which tracks the metadata, and then however much data and space you've got available, you can use for your own individual data that you're storing, whether again it's certificates or private keys or arbitrary data. On startup, the system reads the directories of both of those flashes, and if it can determine which one is the more recent one, it'll start to use that one and then mark the other one as out of date. This handles the case even if you were copying from one partition to the other and it got turned off halfway through, it would pick up exactly where it was before it started the copy. And that way you've always got at least a known valid state. Either the operation is going to be completely completed and everything's happy, or it's not going to be, and it's as if nothing happened. So recovery was key to that. For each of the directories, as well as for each of the objects, we keep track of 3 individual flags, which lets us know, have we started writing this object? Have we written the metadata about the object? And then did we finish writing the data for the object? And by keeping track of which ones are written and which ones aren't, and by always sequencing, writing them in a very specific fashion, when we come back and we examine the contents to recover it, it's very clear, what was valid and what was not. So again, we just kind of listed a sequence. You'd first write this epoch count at the beginning. You'd write the object information in the middle. Come back, write this this third value, which is a start saying, hey, I've copied as much information as I can. And then the fourth at the end, hey, I've finished copying all the information. So by looking at the sequence of what's blank and what's not, we can identify where we are in terms of storing either an object or a directory. Again, this is all code that's provided to try to use Flash devices in a kind of a consistent fashion to store object data. Same type of sequence when we're writing an individual object. The other thing to recognize is that if you write the same object ID number, that will overwrite, quote unquote, the previous object. What it really does is it appends it to the end of the data, and then you will lose access to the previous version. In this way, you can continually update objects without having to do any erases until you run out of free space. And there's APIs to understand how much free space you've got and to trigger a reclamation of old data. Again, trying to minimize the number of write cycles you've got in erase cycles there. Moving on from an API perspective, this is just an example of how you would write a data object. So you initialize your client, set up your metadata. In this case, it's just got a number and a label. In this case, it's just a text label. It's got some data that's going to point to. We're going to add the object into the system using the metadata that we've got, which is ID number 123, and this is my label. I want to update it again, change the data, add the object again, same exact metadata. So it's going to have the same ID value. So it's going to update that data. And again, in actuality, you're going to have two copies of the data. One's the old version, one's the new version. But when you go to access it, you only see the new version. To retrieve this data, again, you would identify by the ID value that you're looking for. You grab the metadata associated with that ID, which would then get you back your label information. And then if you want to read that information, you just pass in the ID value that you've got and pull the buffer right back. So really simple, add object to add data in, read to get the data back. Obviously, the next one is to do a list to understand what data has been stored. Get object is how you grab that, again, that data based on the ID value, the metadata back. And then to destroy objects, you would basically send, hey, these IDs I no longer want, and it will go through, copy the entire partition without copying those IDs that you've listed to reclaim that space. Obviously more details, but a real fundamental, simple object storage. Again, guaranteed to be recoverable, guaranteed to work on finicky flash. Again, this is what we're finding in the automotive industry. So what ports are we currently working on? I'm going to show you a demo off of an RX TC3 today. If I can not run out of time. We're also working on ST's SPC58NN series. Those are our active ports. We do have others coming, but that's the ones that we're hot and heavy working on. The Tricore is a good experiment in terms of porting because it does have cores that are of different architectures, and so it shows that we can run different pieces on each piece. In fact, I'll show a demo where we're running different versions of our wolfSSL engine on it as well, just to prove. But again, this is what we've actively working on right now and have things working for that. From a porting perspective, when we move to a new platform, or if you want to use our system on top of your platform, you only have to implement a handful of hardware-specific interfaces, things like non-volatile memory. We do provide some helper functions for flash-like devices. If you can provide things like read, erase program, blank check, highly likely our library will work on top of it. And then we can provide the object layer on top of that. You'll need to provide crypto hardware interfaces. Again, this is for things like RNGs, key management, and other symmetric, asymmetric cryptos. Again, we've got examples of how we've done this for many ports in the past using our crypto callbacks. From a platform interface perspective, you'd have to understand the boot sequence of your system, how the application cores get reset or marked to boot off of it at a specific start location. And then you may have to control things like shared memory locations, memory translation units, things like that. The configuration that you want to select is selected at compile time as opposed to link time. So in your code, you actually select, hey, these are the libraries I want to use. Here's the configurations of the libraries. And then you work that at compile time. Again, that's an AUTOSAR requirement and not a bad one either. So as an example, this is the kind of a part of our test program where the end game is to provide an NVM object that handles those add object, destroy object types of interfaces on top of a device that looks like Flash. The API that we're using to access that flash, this abstract is called is our flash library, which again is just a sequence of callbacks and types that you would need to manage that. The concrete implementation, in this case, we're using a file on a POSIX file system to simulate flash. And again, it's just this is try to color code it so you can kind of track what you do to select this. So in this case, we would identify, hey, the callback functions that we're going to be using are the ones provided by this POSIX flash file callback. The context that I would need to maintain comes from this POSIX flash file context, and I just allocate one here. Again, we're just doing static allocation just to make sure that we've got it at compile time. We understand this, and by setting this to an empty initializer, this ends up in the BSS, so it's zero initialized up front as well. From a configuration perspective, in this case, the POSIX flash file config requires me to understand what the name of the file that I want to use to spec the storage here, the size of that, and then what byte value I want to use when I mark it as erased. In this case, we kind of made it look like just like a normal flash, a 16K partition, which means the whole flash is, so there's two partitions. The whole flash will be 32K, and when you erase it, it ends up with Fs. Again, from a port configuration perspective, all I've basically done is use these functions on this context using this base configuration. When I go to configure my NVM flash device, in this case, this is an NVM objects layered on top of a flash device. I simply configured saying, hey, this is the set of callbacks I wanted to use, which I allocated up here. This is the context that is going to go with these callbacks, and the configuration is going to be passed when we invoke the initialization is this configuration. So after I've got this NVM flash config, I can use this configuration and place it in my arbitrary generic code for handling any type of NVM object, and I'm off to the races. So I've completely configured from at a compile time of exactly which pieces I'm going to use. So if I was on, let's say instead of a POSIX port, if I was all like on a Tricore, it'd be port Tricore and then whatever the flash file system was or the flash interface was for that. So again, the idea, making sure that we can port to hardware, and then you can control this at compile time. Let me switch gears. I'm going to jump into a quick demo on this. This is a TC367. It's a two tri-cores, one ARM HSM core. I'm going to walk through. I'll show you it running our standard wolf crypt tests on the tri-core, the first COM or the first core that comes up. It's going to run our test in our standard benchmarking program. Then we're going to have the core command the HSM to do the exact same tests and benchmarks. And then after that, we're gonna have the core command the HSM to do a hardware random number generation test, do a sequence of custom hardware callbacks that are only on the HSM. And then we're going to finish off with some low-level hardware crypto tests that the core 0 is asking the HSM to do. Again, this is a technology demo. This is not the full HSM library. It's just a demo to show that we can communicate, we can command, and we can also support two different versions of crypto operations in the same system. Logically, this matches our base design really well. In this case, we're only going to be running a client on core 0. Core 1, we simply leave in an endless loop. It's running a simple bootloader and then sitting there waiting to be in a loop to service incoming requests to gain access to the Tricore's crypto acceleration or local NVM as well. So again, not too much. The only other things that I wanted to point out is that in this case, we're using a set of communication buffers to pass data back and forth, as well as using interrupts to wake up each side when communications are started and finished. Any printf that you see, the Tricore is directly sending us out to a serial port. The HSM, on the other hand, is actually sending its printfs to a communication buffer that the Tricore picks up and then sends out via the serial port. So although you're going to see things that looks like the HSM is printing, it's really not. The Tricore is doing the printing, but the HSM is generating the output. This allowed us to use our bench and crypt test programs completely unmodified on this system. And when you get your own, if you happen to download wolfSSL or wolfCrypt, you'll see that it's the same. The output's exactly the same. Simply configuration compiled to make sure it works on the Tricore. Again, we built this with the RxDev Studio using the GCC for Tricore. We did use our SP math libraries on the Tricores. For the HSM, we built using ARM toolchain. We did enable, we have some Cortex optimized, Cortex M optimized assembly that we enabled in this wolfCrypt. So again, allows us to configure wolfCrypt differently depending on architecture and still have things interoperate. So let me just switch gears real quick to desktop that I've got. Oh, here we go. Let me just clear this real quick, and I'll fire this back up. So I'm just hitting the reset button on my guy here. So at the beginning, the Tricore comes up. It issues a sequence of communication interfaces to talk to the HSM to make sure the HSM is booted and it's now waiting. So it starts talking to the HSM, and then it jumps right into its wolfCrypt tests. Again, these are known answer tests against all of the different cryptography features that are in, oops, hold on, that are in this version on the Tricore that have been run. And again, we'll note that it's reporting it's on the Tricore. We've got wolfSSL version 5.5.0. And you'll see that the set of tests that it runs are specific to what is built into wolfCrypt on the Tricore side. And we'll kind of point out a couple things on that. When we get to the ECC tests, you'll see only certain sizes are built in, and the HSM has the other sizes. This allows us to extend what we had compiled into the Tricore to be handled by the HSM. So again, no answer test to begin with. Below here, we're running a sequence of benchmark tests for each of the different types of operations. We'll pick on this AES 128 CBC encryption on the Tricore. We're getting about 3.7 megabytes per second. Again, that's just software only Tricore by itself from the application core. Move on to some other pieces here. From an ECC perspective, we're seeing the Prime 256 R1 curve being used for its benchmarking. So just recall that size, and we'll move on to the HSM here in a second. So once it completes, the Tricore has completed its benchmark, it then commands the HSM to run the exact same tests locally in software, and then you'll see there'll be some hardware tests in a second. So the output from here now is from the HSM. What it's saying is, oh, hey, I'm running version 5.6.3 on our HSM, and it's plowing through the known answer tests as it goes. And it's right now it's in the middle of an RSA computation, which takes a little bit of time on this HSM. But it allows us to have, again, different configurations, different architectures, but all working together to get the right answers. So in this case, we had a limited set of options that we had compiled into the wolfCrypt on the HSM. And again, I'll come back and we'll pick on our AES 128 encryption. For the software only on the HSM, instead of the 3 megabytes per second, you're seeing about 288 kilobytes per second. So a lot slower. Again, it's 100 megahertz versus 300 megahertz. So we expected it to be slower fundamentally in the HSM in software alone. So as it finishes this off, I'll point out some other features as we go there. It's doing some of those. Now, if you recall, the ECC that we compiled into the Tricore, sorry, that went way too fast. Into the Tricore was the Prime 256 R1 curve. On the HSM, we compiled in the Prime 384 curve. And so this is a good point saying, hey, we can have now two different types of algos on either the HSM cores or the Tricores, and you still gain access to it. Again, this is the Tricore asking the HSM to do this work for us. At the end of the day, we then do a sequence of hardware interface tests. Again, this is just proving that we can interface to the hardware correctly. This key pair solution is generating an elliptic curve key at the Prime 384 curve to be able to get to prove that our key generation does work. This write key test is a non-volatile write. So this is proving that access to the Tricore's local memory are correct. And then after this, we move into a sequence of tests that are using the hardware crypto acceleration on the HSM core. In this case, we're doing a small set of AES encrypts. Again, this is AES 128. That's all the supports. This is a 1 megabyte total. And again, you're getting about 3.4 megabytes per second when the HSM is using the hardware. Again, that's not peak. That's under this very specific case of a small message getting encrypted a bunch of times. So again, it's just a good test to demonstrate low-level hardware interfaces are working. These are, again, are known answer tests as well to prove that we're computing the right answers and we're getting these guys all to work out. So that's the rest of that I did in the, let me switch back to the presentation. Um, Oops, that's not what I wanted. There we go. So the presentation does have the same printouts that you just saw going. I'll just slip through these. If you want to take a look at any of these, we do have other benchmarks and other versions of stuff running, but this just matched what we just demoed as well. All right, and that's the last part of the Tricore. We did want to point out where we're going with this in terms of additional ports. We've had a number of customers come ask us about our support for the RH850 series from Renesas. We think we'll probably work on that one next, specifically the ICU-M, which has a separate HSM core, similar to how these things are being set up in both the Tricore and the SPC58 series. We do want to provide a port that uses a TPM as the hardware crypto backend. Again, recognizing it's not for performance, but for isolation purposes. That also allows us to work on systems that are typically larger, but have secure elements on the side. And then lastly, the TC4 series from Infineon. It's the follow-up to the TC3 series that I just demoed on. We think later this year we'll get a chance to work on those ports. In terms of additional protocols, we'd like to go ahead and finish off our full PKCS11 provider, providing a remote capability for wolfHSM client and server. Second thing we'd like to be able to do is implement encrypted communications between the client and server right now. The implementations we've got are over shared memory, which can be controlled intra-chip. But we see there's a need to provide confidentiality, sometimes even intra-chip would be useful there as well. And we're also taking a look at providing a full AUTOSAR crypto driver that would be plug and play compatible with other AUTOSAR stacks. That's a little harder ask, but that's what we've got on the plate for today. Some other things down the road, we're looking at also adding access controls and then supporting multiple sessions per client. That means you could have multiple users per client accessing in different fashions. In terms of where you can start to take a look at some of these things, we do have some links provided. You'll find a wolfHSM public repo now. We've been moving out of our private repos where we've been doing a bulk of our development, and we're exposing as much as we can as we go. Again, still work in progress, and we're bringing that stuff forward. This is, again, wolfHSM by itself is just the base library. wolfHSM examples is the public versions of the test applications as well as additional features. Some of our targets have large build environments, IDE-based environments, and so we'll be storing this separate from the base library. So when you check out wolfHSM, it's nice and fast, and then you can just do a sparse checkout on the examples to just grab the examples you want to see in the environments you're interested in. Just as a heads up, again, based on vendor NDAs, we can only put certain things out there publicly. And so we are restricted in what we can show, but we do have private ones. And then once we work with you to verify NDAs, we can share the repo contents there as well. Some other pointers, just in case you're curious, base wolfSSL, which you'll need to implement some of the crypto that we've got. wolfboot, which is, again, a companion type of solution. We use pieces of wolfboot, solves kind of a slightly different problem, but in the same vein. Anything that you see that works in wolfboot is a candidate for us to port wolfHSM on top of. And then likewise, our wolf PKCS11 interface library. Again, it's just a provider for PKCS11 using wolfcrypt as the backend. This is what we'll be porting to use wolfHSM as the backend as we go forward. So that's what I had to talk to today. Now it's time for me to ask questions and see if any of this stuff made sense, or if you want me to go back and explain any of it or dig in deeper.
Awesome. Thank you, Bill. I have a couple questions lined up here, and we'll check the Q&A box as well as those flood in. So first question is, How is Wolf HSM different from hardware vendor provided firmware solutions?
Oh, good question. Hopefully, my repeatedly saying extensibility is the first clue, but fundamentally, the idea here is that we provide source for both server and the client. And the expectation is that we find our customers are going to want to put some of their own code into the servers. Existing HSM solutions that are firmware based, we found are closed source or not extensible to the point where you can put your own code in there. Sure, they'll respond to requests, but in the right sequence. But it might be even easier to put the actual code in the HSM core and have it go there. So extensibility is number one. And then the open source is a second big difference from an assurance and quality assurance perspective.
Hmm, okay. Then next here, what are alternative security solutions instead of using HSM?
Another good one. So from our perspective, we see HSM as in a spectrum of secure element solutions. Again, our focus on TPMs and different hardware technologies shows that there really is a wide variety in how you can solve the security problem. So in addition to TPMs and virtualization technologies or things like TrustZone, standalone secure element components exist as well that just do single function, like key storage, that I can also see would be useful in the automotive environment. It may also be that you've got an existing product that does not have an HSM that's available, that by adding in, let's say, a SPI connected or an ITC connected TPM, you might be able to improve its cyber resiliency without having to do a full redesign of hardware and software. So I do think there are some, instead of going to a full-blown HSM, there might be some alternate hardware solutions. And again, we've got experience with a lot of those for a lot of years. So there might be some other ways of skinning the cat. But we do see HSM as a separable security execution context as kind of like the key technology these days to meet the cyber requirements.
Awesome. Thank you here. Next here, does both HSM use or support PKCS number one v 2.2 key storage?
EKCS1 2.2. Oh, yes. So great question. The NVMs can store any kind of data that you want to do. In terms of interpreting the keys, it can support that, provided the storage that you've or the data that you've put in there is well formatted. I would recommend taking a look at tighter formats than ASCII. Binary dir formats is probably the prime. But yes, wolfCrypt does have the ability to understand those certificates and the key material there, interpret that into binaries, and you then be able to use those. So absolutely. Really, from a crypto perspective, anything that wolfSSL and wolfCrypt can do, you can extend and expose into wolfHSM.
Um, cool. Another one here. What are the unexpected challenges to implementing an HSM based product?
I would say the number one surprise to me has been, which may be a feature, frankly, has been the fragility of some of the hardware solutions. It does seem that if you poke these chips the wrong way during development, you will end up with a brick. I think that's good from a long-term perspective, but it was a surprise to me how challenging it was to get development working, make progress without destroying chips. I can tell you there's a stack of busted chips sitting next to me of sequences. I'm not even sure what I did wrong, and that the chip locked up. So from that perspective alone, recognizing some of the expense in development costs that are probably going to get lost as you go down this road, knowing that you've got a path that has been tried and true, you've got example programs. I think that is really the best way to mitigate to mitigate that risk of the fragility of some of these parts. I would say the second thing is the documentation, specifically the things that we found under NDA, sometimes is not matching the reality of what the silicon does. So we found many times where we've got to go back to the vendor and say, hey, you told me if I hit this register this way, I get this result, and you don't, and you end up finding out, oh no, that was a bug, and you got to change your code to do that. So getting a functioning product that's stable is a challenge, and that's again, that was a surprise to me.
Awesome. Well, thank you. I think that wraps up our Q&A section. Yeah, thanks, Bill, for hosting an informative webinar, and thank you everybody for joining the webinar. I'll be sending out a copy of the webinar recording as soon as we get that process, and can provide any PDF slides if needed. Please, again, don't forget to follow us on Twitter at wolfSSL, as well as our LinkedIn and YouTube channel. There's a whole library of all of our webinars. And we'll see you all next week. I believe we have our Wolf Boot webinar going off. Awesome. Thank you. Bye bye.